Hello, I'm Jackson Carver, and I'm going to talk about my research under Dr. Lin on a theoretical method for creating magnetic fields during photoemission spectroscopy. ARPES, Angle Resolved Photoemission Spectroscopy. It's a crucial method for understanding the structure of solid materials, specifically the allowed energy states of their electrons. The method is based on the photoelectric effect, wherein photons are fired at a material, ejecting what are called photoelectrons. What's remarkable about this process, and what ARPES relies on, is that the kinetic energy of the photoelectron and its angle of emission preserve information about its behavior in the solid. By a system of electric lenses and a detector, we can measure these values and determine the electronic structure of the solid. On the right is an example of what the results from ARPES might look like, plotting energy against emission angle. Reading signatures in these results, we can determine the conductivity of a material, whether it's a conductor, semiconductor, insulator, and we can recognize whether it's good to use in a computer chip or in an optical sensor. This is the machine we have in the lab. ARPES is performed in ultra-high vacuum, or UHV, and the pressure in the machine's analysis chamber is kept below 10 to the minus 11 atmospheres. Our machine is multi-purpose, and ARPES is only one of its potential functions. If we were to use a machine for ARPES, we would load the sample into the load lock here, and use the long arm to maneuver it into the analysis chamber here, which is a little obscured in this image. This X-ray gun would fire photons at it, ejecting photoelectrons to be analyzed in this chamber. On the right is the inside of the analysis chamber, with the sample here and the entrance to the detector above it here. However, ARPES has long been considered irreconcilable with an applied magnetic field. This is because a charged particle moving through a magnetic field experiences a centripetal force that causes it to take a helical path. The photoelectrons emitted from the sample would have their trajectories distorted, bending away from the detector. And this is quite a shame, because magnetic fields can have fascinating effects on many materials. For one, magnetic fields are deeply involved in the study of superconductors, materials that can conduct electricity without loss of energy. Right now, most superconducting materials are only achieved at temperatures far below room temperature, but the advent of a room temperature superconductor would revolutionize electricity and computing. A critical obstacle to our progress is that we have no understanding of the mechanism behind high-temperature superconductors, those that can operate above around 70 degrees Kelvin. These superconductors repel weak magnetic fields, allowing them to levitate above a magnet, but their conductivity is suppressed by strong magnetic fields. If we could use ARPES to see how a strong magnetic field disturbs high-temperature superconductors and what effects it has on their electronic structure, we could further our understanding of superconductivity. To make this integration, we want two things. We want a field at the sample site strong enough to induce the desired effects in the sample, and we want that field to decay rapidly in space, so that at a short distance away from the sample, the field is relatively weak. This way, the photoelectron travels through a mostly weak field on its trip from the sample to the detector, experiencing minimal distortions to its trajectory. Our proposal is the Halbach Array. This is a side-by-side arrangement of magnets, where each magnet's moment is rotated 90 degrees from the last. It can be made out of permanent magnets or electromagnets. This arrangement creates a strong magnetic field on one side and a weak field on the other. Moreover, the field decays rapidly in space. So if we place the sample on the strong side of a Halbach array, we can potentially achieve the kind of fields that we're looking for in ARPES. To test the feasibility of using a Halbach array to institute the kind of fields that we're looking for, we simulated the magnetic fields of many different Halbach arrays in the software ANSYS Maxwell. This software calculates solutions to Maxwell's equations with sources of the electric and magnetic fields using the finite element method. We specifically measured how magnetic field strength decays as one moves away from the array. We wanted to test the effect of several parameters on the magnetic field, and thankfully, Maxwell allows for scripting. With this feature, we could create a general array creation script, allowing us to make and simulate arrays of different parameters automatically rather than manually. We started with a Halbach array of permanent magnets. We tested the effects of several parameters of the array on magnetic field strength. Firstly, the magnet density, which describes how many magnets are packed into the length of the array. Here there are 5. This was our most important consideration. Increasing magnet density should amplify the desired effects of the Halbach array. We also tested the effects of the height of the array, its thickness, and its orientation. The orientation describes the direction of the first magnet's moment, which determines all the others. The line extending from the top of the array is the line along which we measured the magnetic field strength. Firstly, and most crucially, we observe the effects of magnetic density on magnetic strength. Here on the right are a 1 magnet array and an 11 magnet array. On the left is a graph of the magnetic field for arrays with different magnet densities. The magnetic field strength decreases as one moves away from the array. In blue, you can see the field of a 1 magnet array, in red, that of an 11 magnet array, and the gray lines represent those in between. A distance of 0 millimeters represents the sample site. By increasing the magnet density, we achieve a significant increase in the field at the sample site. Going from 1 magnet to 11 magnets doubles this field. Moreover, increasing magnetic density amplifies the field's decay over space, with the field moving towards 0 much more quickly, which is promising. We also looked at the field strength for various heights of the array. Increasing the height increased the field at the sample site, but also worsened our decay over space. Increasing the array thickness gave small increases in the field at the sample site, but significantly worsened our decay over space. The analyses of height and thickness, while not directly related to understanding the feasibility of using a Halbach array, are important in the cost-benefit analysis of a potential physical appliance. Finally, we tested the effect of orientation on the magnetic field strength. Sensibly, this had no effect. The magnetic profiles for all 4 orientations are essentially identical. The fields created by a Halbach array depend on how each magnetic moment relates to the last, not on which magnet starts the sequence. Returning to the effect of increasing magnet density, we looked specifically, at the change in the field at the sample site. An 11 magnet array can double this field, but even an 8 magnet array can increase it by 86%. The exact number of magnets to be used in the appliance moves into the realm of engineering. But this increase in field at the sample site, combined with the amplified decay over space, make Halbach arrays seem promising. The appliance we hope to make for use inside an ARPES machine will generate its magnetic fields by electromagnets. So we next simulated an electromagnetic Halbach array in ANSYS Maxwell. Each permanent magnet has been replaced with a long coil of wire. Each of these solid pieces represents many turns of copper wire. In Maxwell, we give each coil an electrical current that generates a magnetic field around it similar to that of a permanent magnet. Making each coil long allows the field in the center of the array to be less affected by behavior at the ends of the coil. We again measured the magnetic field as one moves away from the top of the array, and we observed the same effect as with permanent magnets. Compared to when the electromagnets are all facing the same direction, a 5-magnet array increased the field close to the magnet significantly. In fact, more than tripling it. The rate of decay was made quicker as well. These results point towards the prospect of magneto-ARPES, allowing for the new investigation of many phenomena, including superconductivity. Our next step is to create a physical electromagnet array to gain an understanding of the physical limitations on our design. The array will be similar to that modeled in Maxwell, with long coils of wire used to create a more consistent field towards the center. We want to understand how tightly we can wind the copper wire and what kind of current we can realistically obtain. These findings will help us to refine our design and to understand what kind of field enhancement is realistically achievable. Thank you. Any questions?
So I found it interesting that orientation had no observable effect, but the density obviously is a big deal here. So you mentioned just 11 magnets. Is that like a limitation of your ARPES machine, or can you do 100 magnets, or what point can you extend that?
It was actually a limitation of the software that we used. We ran into an issue with the number of calculations that it was able to perform. But theoretically, there would be an upper limit in how, using electromagnets, and how small we can make each electromagnet while also contributing to the field.
Okay, so you seem rather enthusiastic about using these electromagnets in particular in your final design. So why use electromagnets in place of those permanent magnets?
A lot of the tools used inside of the machine are sensitive to a magnetic field. So using electromagnets allows us to be able to tune the magnetic field that is operating at any time, or to turn it off completely. And this will reduce the risk of a mistake happening inside the machine.
I want to come back to the orientation question. So before you did that experiment, did you have any intuition about that? And can you explain why there was really no effect?
I think my intuition personally, I expected that there might be subtle differences. I was taken aback by the fact that there was almost no difference in any of the 4 profiles. But I think it really speaks to kind of the fundamental symmetry that so long as you've got each magnet rotated 90 degrees clockwise or counterclockwise as you move along the array, the same cancellation on the weak side and the same magnification on the strong side will occur. So it creates the same effect regardless.
So based on your current simulation, how many magnets do you want to use?
Ideally, as many as possible, so that we can get the greatest enhancement and the greatest amplification of decay over space and the greatest increase in the field of the sample site. But we need to move to a physical prototype to see exactly how realistic that is.
So you mentioned possible applications for superconductors. Would it take additional tools to keep the ARPES machine cold enough for superconductors?
Actually, in addition to being able to keep the pressure down inside the analysis chamber, we can already get the temperature in the machine down to such a low degree that superconductivity could occur in high temperature superconductors.